Hi everyone. In this video we're going to continue talking about graphing and solving systems of linear equations. In the last video we looked at several examples of graphing systems of equations, and the second one we found that it wasn't always possible to find the solution to a system of equations just by looking at its graph. So instead we'll now look at two algebraic methods. All right, so here's the first one: solve using substitution. Right? So what we're trying to do is find the single point that makes these two equations true. Right? On a graph, that looks like the point where the two lines represented by these equations, where those two lines intersect. All right, so what you want to do is solve one of these equations for one of the variables, either x or y. So in this case, I'm going to focus in on maybe either this x or this y, terms that don't have coefficients, that just have a coefficient of 1, okay, like 1x or negative 1y. Those are going to be the easiest to solve for. So if I solve this equation for x, basically I want to rewrite it with x by itself. So I'm not solving for a numerical value for x, but just getting x by itself. So what I want to do is subtract 3y from both sides, and then that isolates x. Okay, and then I get x equals negative 3y plus 8. Alright, and then what I have now is an equivalent expression to x. So this equation is saying that x is the exact same thing as negative 3y plus 8. So now what we want to do is use the second equation. This is equation 1 and equation 2. And in this second equation, I'm going to replace the x by this expression that I now found that it equals. All right. So instead of an x, I'm going to put a parentheses. Okay. And then I fill that in with the equivalent value for x, negative 3y plus 8. And now what I have is sort of a hybrid of the two equations. So this represents the entire system, but notice I've also eliminated the variable, and now I just have a y in here. So now I can just solve this like I would a normal linear equation, and I want to solve for a numerical value for y. Okay, so first we want to use order of operations, try to simplify as much as possible. So this one I can distribute first, distribute the 2, and get negative 6y plus 16 minus y equals 9. Okay, combine like terms. I have negative 6y and negative y is negative 7y. Alright, subtract 16. Okay, so now I'm actually solving. That gives negative, let's see, I'll put this up here. Negative 7y equals negative 7, and then divide both sides by negative 7, and we see that y equals 1. Alright, so I know y is 1. Now I need to find x. So to find it, you can go back to any of the equations that have both an x and y in them. Alright, so I could use this one. Alright, and that's probably the fastest since x is by itself. But if you're worried that you made a mistake there, okay, then go back to one of these two original equations, right, just in case you made some sort of a mistake when you got this equation. Alright, so I'll use this one and substitute in 1 for y, and then just use order of operations to simplify and find the value of x. So x is negative 3 plus 8, or 5. Okay, so here's the solution, 5, 1. Now this should look fairly familiar if you watched the last video, because we already did graph this system of equations, and we did find graphically that the solution was 5, 1. Okay, let's try this one. 3x minus 4y equals 10, 2x plus 3y equals 1. Now here, neither x nor y has a coefficient of 1 in the equations, so I don't really see any that seem particularly easy to solve for, so it's really up to you. Let's do one example of solving for y, because it doesn't have to be for x. And I could also start with either equation. So let me start with equation 2 this time, and I'll try to get y by itself. So first I'm going to subtract 2x from both sides. Okay, and then divide by 3. So we get negative 2/3 x plus 1/3. Okay. Now I need to substitute this into the other equation, into equation 1. So I have 3x minus 4, and then instead of y, I'm going to replace it with the thing that I just found that y equals, with negative 2/3 x plus 1/3. Okay. Use order of operations to simplify next. So this is 3x, and then I'm going to distribute a negative 4. So negative 4 times negative 2/3 is positive 8/3 x, and then negative 4 times 1/3 is minus 4/3. Right. I can combine like terms. Let's see this. 3, I'm going to combine 3x with 8/3 x, so I need a common denominator. 3 is 9/3. Alright, so 9/3 and 8/3, that's 17/3 x minus 4/3 equals 10. Okay, so that's what we have so far. Alright. And then I just need to get x by itself to actually solve. So I'll add 4/3 to both sides. So 17/3 x equals 10 plus 4/3. Okay. And 10 is 30/3. So 30/3 and 4/3 is 34/3. Alright. And then I can either, to solve for x, I can either divide by 17/3, or what I like to do with fractions, multiply by the reciprocal. So if I multiply by 3/17, okay, then that's going to cancel this out and leave me with 1x. Okay. Now here, this is pretty nice. The 3's cancel when I'm multiplying fractions. And then I just have 34 divided by 17, which is 2. So even though there's messy fractions in the middle, we actually had a really nice integer answer here. Alright, so now to find the value for y, I just need to substitute x back into one of these equations, right, or the one that I erased that had y in terms of x. So your choice, you can choose either one. I will choose the second equation, alright, and then replace x with 2 and solve for y. So we have 4 plus 3y equals 1. Subtract 4, 3y equals negative 3, and then y equals negative 1. So my solution is 2, negative 1, and I can write that as a point. Okay? And now as a quick double check, see if this fits in the other equation. So I know 2, negative 1 works in this last equation because I just worked that out. But if we wanted to check and make sure it's a solution to the system, it also has to make this first equation true. So let me double check. I'll do 3 times 2 minus 4 times negative 1, and hopefully that equals 10. Okay, and we get 6 plus 4 equals 10. Yes, that works. Alright, a second algebraic method, solving by elimination. Okay, so in this case, what we want to do is try to add these equations in such a way that we get rid of one of the variables. Right? So like right now, if I just straight away tried to add these, if I added all the like terms, I'd have 5x and 3x is 8x, negative 2y and 5y is 3y, and then 10 minus 56 is negative 46. So what I end up with is an equation that still has an x and a y, neither one has been eliminated. Okay? Now there's a trick. In order to get one of them to eliminate, what we need is for either the x terms or the y terms to have the same coefficients, but the opposite sign, plus or minus sign. Okay, so notice right now, the y's at least have the opposite sign. It's just the numbers that are a problem. Okay, but like if this was a 2, then I'd be in good shape because negative 2y plus 2y would be 0, and then those would eliminate when I tried to add. So how are we going to get the coefficients to be the same number? Well, usually what we do is we multiply one or both equations as needed to get that same number. Okay, and remember that this is the multiplication property of equality. I am allowed to multiply both sides of the equation by the same number without changing the equation or something like that. Okay, so usually what we do is multiply by whatever's needed to make these the least common multiple. Right? So if you look at the least common multiple of 2 and 5, just ignoring the plus and minus sign for now. Okay, well, multiples of 2, 2, 4, 6, 8, 10, etc. Okay, multiples of 5, 5, 10, 15, etc. And then the least common multiple is 10. All right, so ultimately I want to try to get the 2 and the 5 to be a 10. So if I multiply the first equation by 5 and the second by 2, those are the numbers that are needed to make 10s. Okay, so I'm going to go through and distribute, multiply everything by 5 and then everything by 2. So we end up with two new equations, 25x minus 10y equals 50. A common mistake students make is to forget to multiply the 10 by 5, so don't forget that. And then the second equation, 2 times 3x is 6x plus 10y equals negative 112. Alright, so now watch what happens when we add these. 25x plus 6x is 31x. Negative 10y plus 10y is 0y. That's great. And I'm not even going to bother to write that. And then 50 plus negative 112 is negative 62. Okay, so again, I've used a different method, but I've still combined those two equations in such a way that I get a new equation that just has one variable, and now I can solve for that variable. So I have 31x equals negative 62, and then I can divide both sides by 31 to see that x equals negative 2. Now same thing to find y, I just plug this back into either of the original two equations. So if I choose the first one, then I get 5 times negative 2 minus 2y equals 10. So that's negative 10 minus 2y equals 10. And then start solving for y. So add 10 to both sides. And then divide by negative 2. Okay, so the solution is negative 2, negative 10. And again, you can check this. Substitute those coordinates into both of these two equations and make sure that the two equations are true. Alright, we'll end this video with an example of graphing a system of equations with multiple equations, more than two, and instead of just finding a solution, the point of intersection, since we actually have 4 different lines here, let's try to find the coordinates of all of the intersection points. So perhaps some of these will be easy to see graphically, and then perhaps others will need to use either elimination or substitution to find. Alright, so the first one, 2, 3, 6, right away I noticed that these are all, 2 and 3 are factors of 6. So this looks like it's going to be easy to try to find the intercepts. So I'm going to start with that. So if I make x a 0, then I have negative 3y equals negative 6, and then y is negative 2. Okay, so I have the point 0, negative 2 makes that equation true. And similarly, if I have y as a 0, then I end up with 2x equals negative 6, and then x is negative 3. Alright, so I can plot those 2 points, 0, negative 2, and negative 3, 0. Now from the graph I can see the slope right away. Right, from one point to the other I'd have to go over 3 and then down 2. So what you might want to do to be more accurate is just go over 3, down 2 a few more times, and just find some other points on that line. Right? I could also go up 3, or I'm sorry, up 2 and back 3, going this way to the left along the line, and find a few more. Okay, so there's my line. And since I have so many of them, I'm just going to label these like I did before with some different colors and different stars or symbols. Alright, the next one, the coefficients are 1, so also this is fairly easy to do just with the intercepts. If y is 0, then x is 7. And if x is 0, then y is 7. So those are my two intercepts. Okay, 7 on each axis. Okay, and then I'll put a line through those. Okay, close enough. Alright, then y equals 2. This, because it only has one variable, is either going to be a vertical line or a horizontal line. And this one is horizontal. So remember that y equals is horizontal, x equals is vertical. So I want to go to the y-axis, find where y is 2, right here, and then just draw a horizontal line through that point. Alright, let's see. Here we go. Okay, and then let's do red for the last one. X equals 1. So find on the x-axis where x is 1, and then just draw a vertical line through that point. Okay, there we go. Alright, so now I need some intersection points. Well, there are quite a few of them. Some of these we can find fairly easily. So for instance, this point, okay, it's right where two easy lines cross. So I can see that that point is 1, 2. Okay, that's that one. I have another point right here, and I definitely know the y-coordinate because I know that it's on the line y equals 2. So I know the y-coordinate is 2. Now I don't know the x-coordinate, but if you'll notice, that point is on the blue line. So what I can do is go to this blue line equation, and if I substitute in the y-coordinate that I know, if y is 2, then that allows me to solve for the x-coordinate, and I know that x is 5. Alright, so basically what I'm saying here, if you're trying to find this point, you look at the equations for the two lines that it happens to lie on, which would be the yellow one and the blue one, and then you can use some combination of either looking at the graph, or elimination, or substitution to try to find those coordinates. So in this case I just use substitution. It's pretty easy since we know the numerical value of y. Right? So when I make that substitution, there's not very much solving to do to find x. Alright, so 2 points down, a couple more to go. This point, alright, I don't really know the y-coordinate. Looks like it's maybe a decimal or a fraction, but since that is on the vertical line x equals 1, right, it's on this line and then the green line, then I know for sure that the x-coordinate is 1, and then I can just substitute that into the other equation, the green one, to solve for y. Right? So I'm going to substitute in 1 for x and solve for y. Okay, so I get 2 minus 3y equals negative 6. Subtract 2 from both sides, and I get negative 3y equals negative 8. And then divide by negative 3. And let's see, something went wrong here because that's a positive number. All right, y can't be 8/3, so maybe I have an incorrect sign there. Okay, so let's double check that one. Okay, and let's see. Let me just retry that. So when x is 1, I have 2 times 1, 2 minus 3y equals -6. All right, that looks okay to me. So what I'm wondering is if I graphed that line incorrectly. Now I could go and edit this video and redo all of this, but I think I'll let this one stand with the mistake, so that way we can talk about what happens if you make a similar one. So if you get something there that doesn't check out, all right, so I noticed this can't be 8/3 because that point is supposed to be, this point is supposed to have a negative y coordinate. So if that happens, then first thing I did is check the arithmetic, and that checked out. When I plug in 1, I do get 8/3. Right? So the issue is probably with this green line, because I'm fairly confident I graphed the red line correctly. So I'm going to go back and look at that equation. Unfortunately, that's the first one that I did, so that's kind of annoying. But let's check the intercepts again. All right, so I know that the x-intercept, when y is 0, x is -3. Okay, that looks okay to me. All right, and here I think is the mistake. When I substitute in 0 for x, then the y should actually be a +2 and not a -2. Okay, so this green point should actually be up here. So that's going to change quite a bit. So I'm going to pause this and fix this graph, and then we'll restart and look at what that does to some of these intersection points. Okay, so I fixed that green line. All right, and fortunately it hasn't changed the 2 points that I found, but it did change where this green line intersects some of the other equations. All right, so let's record what we know so far. All right, I knew this point, which is 1, 2. I know this point, which is 5, 2. All right, now I have 3 intersection points for the green line with some of the others. All right, I have this one. Okay, and that's crossing the y-axis. So I know for sure that the x-coordinate is 0. And then I just need the y-coordinate. All right, and I could use slope to know what this is, right? Or the fact that I already graphed this line using the intercept. That's the point 0, 2. Okay, now I don't know if you can see in the video, it might be too small, but if you make this graph on your own, you should see that the green line crosses the red line at some sort of a decimal value. Okay, so what I want to do is pair those two equations together, the green one and the red one. Now this again I can do by substitution. I know x equals 1, so then I need to just substitute 1 in for x into that equation, which is what I was attempting before. Okay, and then solve for y. So we ended up with -3y equals -8, and then y equals 8/3, which is 2 2/3, and that does look a lot closer to the point that I actually see there. Okay, so we've done that one and then that one. Now the green line also crosses the blue line right here, so I want to take a look at that. Okay, so look at the green line and the blue line. And I have a guess. It kind of looks like 3, 4 to me. So I'm going to substitute those coordinates in and see if those work. That certainly works in the second equation. 3 plus 4 is 7. So let me check the first one. 2 times 3 minus 3 times 4. And see if that equals -6. So that's 6 minus 12, which is -6. Alright, that checks out. So we know 3, 4 is that intersection point. If that hadn't been easy to see, or if that had turned out to not be the correct solution, then just pair these two equations and use either substitution or elimination to find their intersection point. Alright, what else do I have? I think I've done all of the yellow line intersection points and all of the green line ones. The red one, I've done most of those, but I think there's one more. I want to look at this point right here, okay, red and blue, where they intersect. Red and blue. Alright, so I'll use substitution again. I know x is 1, so I can substitute that into the other equation, and then I find that y is 6. Okay, so I've done green, red, yellow, and then blue. I just have, no, that's it, okay. I was thinking here, but this intersects an axis, not another line. Okay, so those are all of the intersection points. Alright, here's another one that I will leave for you to do as practice, but make yourself a coordinate plane similar to this one, and then try to graph those 4 equations and give the coordinates of the intersection points. Okay. Now you're just going to look at pairs of 2 of them, so anytime you have an intersection point, go back to the 2 equations that correspond with that. Say it's maybe these 2. Okay. If you can see it from the graph, then just double check, plug the point in to make sure that that works. If it, make sure that that point that you think is the solution makes both of these equations true. If it doesn't, then use substitution or elimination. All right. Look for horizontal and vertical lines. All right, as sort of a hint there. Okay, and see what you can do with that. Okay, so a review from this video. We talked about solving by substitution and elimination, graphing systems of 2 lines, and then graphing systems with multiple lines. Okay, so we did 4 here. We could have done 3 or 5 or anything like that. Okay, that's it for this video. That's section 7.2 from Math in Our World. Thank you for watching.